Have your calculators out and ready to go. All right. So just to sort of recap, because I know it's been a while, we were talking about polar and rectangular coordinates. And we said that we can sort of change back and forth between polar and rectangular coordinates by using these identities that we've already developed. So if you have a coordinate in rectangular or Cartesian coordinates, x, y, you can change it into r theta coordinates in polar coordinates by looking at the Pythagorean theorem. R is equal to plus or minus the square root of x squared plus y squared. And you can use tangent of theta is equal to y over x. And you just might need to move that theta into a different quadrant, find that reference angle. So that's going to be the way that, probably the easiest way that we can change rectangular coordinates to polar coordinates. To go the other way around, if you have something in polar coordinates, finding rectangular coordinates is super easy. Now that you know trigonometry, you can just take r cosine of theta to find the x coordinate and r sine theta to find the y coordinate. And we've been doing this all along with vectors, with polar coordinates, and things like that, or with complex numbers, I should say, the complex plane, and things of that nature. So we've done a lot of examples here. All right. Last time we sort of ended up with this example, and I just want to briefly review the polar axes. So the polar axes are made up of concentric circles, which sort of give you the radius or the distance away from the center point. And if you remember this from last time, the center point is called the pole. It actually has coordinates 0, 0. And it's made up of these sort of lines that emanate from that pole. And those are going to give you the angle from this positive x-axis. But in polar coordinates, we call this the polar axis. So we start at this polar axis and we sweep counterclockwise to give a positive angle or clockwise to get a negative angle. So for instance, and we did this last time, but I just want to sort of recap. If I wanted to label r, with polar coordinates, we are given these coordinates in terms of the distance from the pole and the sweep of the angle in the polar axis from the polar axis. So if I wanted to plot that point r, I would go out 2 away from the pole. So I'd be on that concentric circle, and I would sweep pi over 3 or 60 degrees, and that would be my point r, which is at 2 pi over 3. So that's how we could plot things on the in polar coordinates with something like q. Again, I can think of this as r and theta, so that's how the coordinates are given. So this time, theta sweeps 45 degrees from the polar axis, and if it's positive, we go counterclockwise, so that's all the way up here. And then since that r is negative for q, we actually flip through the pole and we go 3 units in the other direction. 1, 2, 3. So this would be our point over here. Actually, no. I was looking at the other one, sorry. We would flip through that and would be going down the 45-degree line. Let me try again. 1, 2, 3. There we go. All right, so that would be our point Q. So our radius or distance away from the pole is 3, but it's in the opposite direction. So we flip or reflect across that pole, and it's going to be a 45-degree revolution there. Okay, but we also said, hey, we can actually, unlike Cartesian coordinates, we can actually find all sorts of different coordinates for polar coordinates. So I could label, for instance, Q or R or P in different ways. So I could use different coordinates to represent them. I could use, for instance, a double rotation. I could use a negative radius. I could use a clockwise revolution. So I could do all sorts of things to label these points in infinitely many different ways. Another thing I want to do is I want to try to label these over here in my, so if I have a point in the polar coordinates, I want to be able to plot it in the rectangular coordinate system. So I think let's go ahead and start out by just converting some of these over. So what I'd like you to try to do, if you don't mind here for a minute, just to get us back in the swing of things, I want you to convert Q and R to rectangular coordinates. So we're going to start there and then we'll plot those. So if you remember our conversions, we were talking about for X, you would just do R cosine theta, right? And for Y, the Y coordinate, you would just do R sine theta. So I'd like you to take a couple minutes and try to do those, please. Theta, theta, there we go. So when we're converting things from polar coordinates to rectangular coordinates, you want to use these two identities to convert those over into X and Y coordinates. And for Q and R, you should be able to compute exact coordinates. So I'd like you to try to do that. So we're looking for two X and Y coordinates. And from the polar graph, you should see that the Q and R will be in the same quadrants as they are in the rectangular coordinate system. So I'm going to give you just a couple more minutes to see what you can do here. Okay, I'm going to check out and see if anybody else joined us. I saw Kai join us. Welcome, Kai. And I saw Nicholas join us. Welcome, Nicholas. I think that's it. Everybody else, I think I already had. Yeah. Okay. Okay, so we're trying to keep my eye on people and see if they're done. I see a few people looking down still. Give you a little more time. Okay, so that is 3 minutes or so. Does anybody need 1 more minute? No? Okay, all right, great. So I would like you to type these in as ordered pairs in the chat. We'll keep them exact. So if you have like a square root of 2 or something like that, just write SQRT of 2, or give me something to make me know it's like the square root of 2. So we're going to be looking at Q first. So we'll type that in chat, and we'll send it in 3, 2, 1. Please send it. Great. Thank you for participating. I would just want to make sure that we're on the right track. Okay, we got a little more than half of you in there. There's 7. We'll go for 11, hopefully. 8, 9, 10. Okay. All right. There's 1 more person. All right. Well, let's go ahead and take a look. So, okay. So -3 square root of 2 over 2. -3 square root of 2 over 2. All right. Same thing for Chang. Let's see. Okay. -3 divided by square root of 2. -3 square root of 2 over 2. -3 square root of 2 over 2. So yes, so these are definitely going to be the same coordinate. Nice. So yeah. All right. Excellent. Very good. So I think that it's safe to say that we could write this as in 2 different ways. So we have -3 square root of 2 over 2. And the same thing over here. Or if you would like to write that as -3 over root 2, that's going to be the same exact number. All right. So I'm going to type this in my calculator just quickly to see what an approximation to that is. So let's see. 3 square root of 2 over 2. So that's about 2.12. So it looks like if we were plotting on the rectangular coordinate system, that would be about right here. So that would be the point Q there. And when you look at it, compare it to the complex plane, or not the complex plane, but the polar coordinates, sorry, it looks like it's about in the same place. Now, my Cartesian coordinate system isn't as spread out as the other one. So that's it right on where you would have it. So it looks like everybody got that one for the most part. Are there questions there at all? Okay, let's take a look at this next one then. So I want you to send R. So please type that in the chat. So this one, we're thinking we know it's in quadrant 1, so both of those should be positive. So in 3, 2, 1, send it. All right. 4, 5, 6, 7, 8, 9. Wait a minute. 10, 11. All right, great, everybody. So 1, 2 over square root of 3. Ugh, I made a mistake. A new message. 1 square root of 3 over 2. Okay, 1 square root of 3. 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 Square root of 3. 1. 1 square root of 3. Okay, so it looks like for the most part, we have 1 comma square root of 3, and that's exactly what I had. So the only thing you have to be careful out here, nice job, is to multiply that value of cosine and sine by the 2. So when you're looking at the coordinates for R, the X is going to be that r, which is -3 for, no, sorry, 2 for r, cosine pi over 3. And then the last thing to be careful about, remember in radians, pi over 3 is actually 60 degrees, and pi over 6 is actually 30 degrees. So it's easy to make a mistake there if you're not careful for sure. So the cosine of 60 degrees is 1/2. So when you take 2 times 1/2, you get 1. And the sine of 60 degrees is √3/2. So when you take √3/2 times 2, you get √3. Excellent. So this coordinate will be in the Cartesian coordinate system, 1 comma √3, and √3 is about 1.732 approximately. So 1 comma √3, nice work. And that is going to be this coordinate r. And again, when you look at this one compared to the one over here, it looks pretty much in the same place, but that Cartesian coordinate system on my screen is a little bit shrunk down. All right. Excellent. Are there questions there? All right, so this is the skill that you want to have going into the final. You want to be able to convert back and forth. And really, it's just another application of this trigonometry. All right. Another thing that we want to do is sort of like look to see if we can plot these things in polar coordinates. Now, when the time comes where you're using polar coordinates, you'll be going over this all again, but it'll be nice to know that you have a basic grasp of this before you see it again. All right, so I'm going to give you one more practice for this. We have 2 coordinates here that we would like to convert, one to rectangular coordinates and one we're going to convert to polar coordinates. So I'm going to give you a little bit of time here to convert the first one to rectangular coordinates. That's what we've been doing. But the second one, I want you to convert back to polar coordinates. So remember those identities that we're using. And also, I think that first one, you're going to be able to get that exact. The second one, you're probably going to need to use your calculator. So while you're doing that, I'm going to go ahead and plot these. And we'll sort of share these in a few minutes. So I'm going to try to plot these for you all. And you're going to actually crank these out and convert, if you would. So the first one, I have 4√3 and -pi/6. That's around here. So I want to find that point. And then the next one, this is actually in rectangular coordinates. So that one's going to be easy for me to plot. Okay, so that's easy to plot in rectangular, but we'll want to look for it in polar coordinates here. Okay. So what I've really done here is plot them for you, and you're going to go ahead and convert those, please. Here we're looking for X and Y. And here we're looking for R and theta. So yeah, so some of them don't come out exactly, but some of them will. And this is another one of those beautiful examples where knowing your trig values, your mastery trig values help us out. Yeah, we use that through the whole course, just like I promised. So yeah, so for the second one, you'll definitely need that calculator or something like that with Desmos to probably you'll be able to get that R exactly, but that theta you might need a little help with. Even like a Google calculator would probably be enough to give it to you. Right. Okay. I appreciate you working on these because it's only when you make mistakes or get them right that you know what you're doing. And this is a safe place to learn here. I'm sort of looking at people. Some people are still looking down, so they're still working. That's great. Keep going. Okay, there's about 3 or 4 minutes. Does anybody need another minute? Need another minute? Yep, go ahead. You bet. Thanks for letting me know. Okay. All right. I think everybody's ready now. So if you would, so the first ones we're going to type in something in rectangular coordinates. So please type that in the chat, and then we'll send it here in 3, 2, 1. Send it, please. All right, there's 2, 2, and 2, and 3, 4, 5, 6, 7, 8, 9, and 11. All right, excellent. Let's check it out. Okay, so -6, 2 root 3, 6, -2 root 3, 6, -2 root 3, -6, 2 root 3, 6, -2 root 3, 6, 2 square root of 3, 6, -2 square root of 3, 6, -2 square root of 3, 18, -2 square root of 3, 6, -2 square root of 3, 6. Okay, so definitely 6, -2 square root of 3 seems to be rising to the top. So it seems like when you look at where that's plotted, you know there's going to be at least one negative value there, and it will be the y. And most of you had that. So that's another way to sort of check these out. If you can plot them, at least you'll have a really good idea of which one's negative and which one's positive. All right, so here, if you know your special values of the triangle, then you're going to be in good shape. So, you know, usually we would use r cosine of theta, and we can do that, and r sine of theta, but notice, I'll show you this alternate way to do it. So since we know our values here, really this is going to be the y coordinate that I just drew there, and this will be our x coordinate. This is a 30, 60, 90 triangle. The pi over 6 is going to be our 30 degrees. So that means that this is 60, and this is our 90. Our hypotenuse is 4 root 3. So the small side will be half of that, and that will be right here. And then the larger side will be root 3 times that smallest side. So that's going to be the x coordinate. So 2 root 3 times root 3 times root 3 is 3, 3 times 2 is 6. So this is 6, just like y'all said, and this one has to be negative root 2 root 3. So this will be 6, negative 2 root 3 in rectangular coordinates. Excellent. And that's the only thing it can be, because rectangular coordinates are unique. So you should get the exact same thing if you did r cosine theta and r sine theta. All right, nice job. It seems like the majority of you got that. Are there questions on that one? Okay, all right, so I'm curious on this next one. So notice this next one, it is in the third quadrant. So when you type this in, we're going to be using polar coordinates. So it's possible that we could get different answers and they'd all be right. So I need to be in my game here. So I'm going to have us type this in. So polar coordinates, and 3, 2, 1 for the second one. Please send it. All right, 1, 2, 3. Right off the bat. 4. I know these are sort of a pain to type in. We could do it easier. There's 5, 6. But I appreciate you doing it, because then we can see what some, you know, you can say, hey, everybody got it right, or here are some common mistakes we need to look out for. That's another good reason for doing this when we're in this environment. All right, I've got 9. 2 more brave souls out there. Maybe. All right. Okay, so this one was tougher. Totally agree. Let's see what y'all got. So square root of 13, 146 degrees. Square root of 13, 214 degrees. Square root of 13, negative 124 degrees. Square root of 13, 146. Square root of 13, whoops, 6.93. I'm guessing that's the square root of 13 and 30 degrees. Square root of 13 and 214. So this is sort of all over the map. Negative square root of 13 and 34 degrees. Square root of 13 and 146 degrees. square root of 13 and 214 degrees. All right, so very, very interesting here. And this is sort of what I got in my other class too. So yeah, so the hypotenuse is always sort of the easiest one to solve for, I think, because of course it's based on the Pythagorean theorem, right? So this is just -3 and -2. So the hypotenuse would be square root of 9 plus 4, and that is square root of 13. So exact square root of 13. Theta, to get theta, I'm guessing you took inverse tangent of opposite over adjacent, right? Maybe. Maybe. And I did that, but I don't have it right yet. So I should have been doing that again. I saw something, oh crap, I'm in radian mode. Ah, okay. I saw something look familiar. I think it was about 33 degrees or something like that. 33.7 or 69. So, you know, I didn't really say where to round it to. I'm just going to round mine to 33.7. So things close to that would be okay. And here's our problem though, right? So this is going to get us somewhere in the first quadrant, right? But it's not going to get us where we need to go in that third quadrant. So we can use this as a fine reference angle, but it's not going to be the angle that we're going to use for this polar coordinate. It just won't get us there. Unless you were like Grace, who was like, hey, I'll just flip it through the flip it through the pole, and that will work. So one of these things would work. I like that. And maybe another one of you did that, is negative square root of 13, 33.7. So that's just finding this radius and taking that angle and then flipping it, making that radius negative. So it flips it through the pole and bam, right where you want it. If you made it a positive square root of 13, then we have to find that angle in quadrant 3. And that just has us doing 180 plus that, right? So 180 plus that. And I did see several of you adding 180 on. I think that gave us 213. Is it 213? Can I do that math in my head? Let me look down at my paper. 213. Yeah, 213.7 degrees. So if you did it that way, hey, that works as well. And that will give you the positive, but your radius would have to be positive there. So there's a 213.7 or close to that. So either one of these would work. Those are the two most popular answers. Now there are infinitely many more that will work. If you had like an angle of 146 or something like that, then you're in quadrant 2.
I messed that up.
That's okay. That's okay. But that's, I mean,
like, well,
hey,
now I know what to remember to check.
There you go. There you go. So you can sort of see that it might be important to plot these just to see where you are, especially when you're converting from rectangular to polar, right? Because you're not as familiar with the polar coordinates there. Nice job, everybody. I really appreciate you helping me out. Are there any questions there? Okay, so those are the skills that are going to be the most helpful for you for our class, for our exam coming up. Okay, so now we're going to be looking at converting these equations over to maybe, oh yeah, from polar to rectangular. So we are given equations and polar coordinates, and we sort of want to know what they look like in rectangular coordinates, or we can actually convert these over. So the identities that are going to be helpful with converting rectangular coordinates to polar coordinates to rectangular coordinates are, of course, x squared plus y squared is equal to r squared. So that will give you something involving r, or tangent of theta is equal to y over x And of course, we know that if you have an x, you can just sub in r cosine theta. And if you have a y, you can sub in r sine theta. Or if you're going the other way, you look for r cosine theta and r sine theta. So when I'm looking at this polar graph here, that's the way to describe a polar graph, a polar equation there. I see that r squared, that stands out to me. And I say, okay, I need to get everything in terms of x and y. I need to get the r's and thetas out of there. So when I see that, I'm just going to sub in x squared plus y squared for that r squared. And that's x squared plus y squared is equal to 9. So this is going to be my equivalent Cartesian coordinate graph. Do any of you know what that graph would look like if we plotted it?
A circle with radius 3.
Nice job, Connor. Yeah, so it looks a lot more familiar probably in its old Cartesian coordinates form, right? It's sort of like the distance formula, right? So x squared plus y squared is equal to the distance squared. So that really says, you know, if I go take the distance between 0 and the origin, sorry, 0 and the point, the origin and the point, I'm going to sweep out 3. But you can think of it in terms of this equation. Like even if I took, even though it's not a function, if I took like plus or minus the square root, I would get r is equal to plus or minus 3. So that would say, hey, I'm going to go out here at a length from the pole of 3, and theta is just going to be free to sweep around. So I'm going to sweep out this circle. And whether I go in the positive or negative direction, it's just going to keep sweeping. So that's what the graph of r squared is equal to 9 would look like. Okay, so the second one is going to take a little massaging. We could actually write this one as a polar function, but we might see if we want to convert it over that if we distribute that r through, you would have r cosine theta plus r sine theta is equal to 3. And the reason I might want to do that is because, hey, over here, I have those values. So r cosine theta is x, r sine theta is y. So that turns over to a Cartesian graph coordinate equation really easily. And in fact, I can solve that in terms of a function. So this one's just going to be y is equal to negative x plus 3. So this Cartesian coordinate function is similar to this one here, or the original one. So what will the graph of that look like?
It'll be a line with a negative slope and an intercept of 3.
Exactly. Nice job, Grace. So this one's a lot easier, to me at least, to interpret in its Cartesian coordinates, right? So I mean, I could actually solve for this in terms of its polar function. So its polar function would look like this. So this is an equation of a line in polar coordinates. Boo. Ugh. It looks gross, right? It doesn't look as aesthetic as our linear function that we know all about in Cartesian coordinates. So these are actually the same thing, but one is in polar coordinates and one is in rectangular. So if I was to plot this, Grace, you're absolutely right. I would go up 3 and have my coordinate, or my y-intercept there is 0, 3, and then I would have a line with -1 slope. That's it. Very good. So I guess the moral of this story is if you have circular functions, as we talked about, they're easier to describe in terms of polar coordinates. Whereas if you have a linear function, most of the time, it's easier to describe that in the Cartesian coordinate system. So there's pros and cons of each system there, for sure. All right. Any questions? Okay. So the last thing we want to do is we want to sort of look at these polar graphs. It'd be pretty cool. So that's sort of what your Desmos project is going to do. It's in assignments in Canvas. So the Desmos project is going to lead you through converting coordinates to polar coordinates. And then it's going to talk a little bit about what we've done today, but it's going to have you experiment with some of these nice pretty graphs that we can get in polar coordinates. So I'm I think I might skip over a lot of this stuff. I think we've done a lot of this. I don't know. I guess we could do another one. Look at that 86. That looks ugly, doesn't it? So what if I wanted to write 86 in terms of polar coordinates? So that would be a case where we have something in rectangular coordinates that we really couldn't express as a function for sure. But with polar coordinates, we might have a chance. So if I was doing that one, what I might do is for x squared and y squared, x squared plus y squared, I might plug in an r squared. And remember, if I'm trying to turn this to polar, I need to get rid of all the x's and y's and turn them into r's and thetas. So I do know that x is r cosine theta, y is r sine theta. And so if I'm trying to solve this for r, there might be an r squared I can factor out of the left-hand side. And then I could actually solve it for r squared by dividing by the rest of the cosine and the sine.
Where did the r squared plus go?
I factored it out.
Oh, okay. I see now. I'm sorry.
Okay. No worries. I did that pretty quickly, didn't I? Yeah. So I needed to get that r squared by itself. Thank you for stopping me there. Yeah. So I needed to pull that out so I could solve for r. So I pulled that out of both terms. I'm just left with the 1 there and then the cosine sine there. Apologize. And then I can divide through by that whole grouping. And I have something like r squared is equal to 1 over 1 plus cosine sine. And then here, I can go ahead and take plus or minus the square root. Here's sort of the nice things about polar coordinates, though, as opposed to rectangular coordinates. When I have an r squared, we know when we take square roots, we're supposed to take the plus and minus. But really, with the plus, it's going to sweep things out in the positive directions. With the minus, it's going to sweep things out in the negative direction. So you might have to use different values for theta, but you'll still get that graph, no matter if you take the plus or minus in polar coordinates. So I guess the last thing we can do is just get rid of the minus, and square root of 1 is 1. So this graph will turn out to be, the function will turn out to look like this. That's the function, and that would be choice number C, letter C. There. Now, sort of in anticipation of graphing these things, if you have your calculator with you, you can actually graph something like this. So all you have to do is go into mode. And what I would do is switch got your calculator with you? Switch your function down there, function to polar. And I think I'm going to switch my mode back into radian. So from degree to radian. So we're going to be using polar if you're following along with me here. When you plug in y equals, there'll actually be a place to put in, it'll be r is equal to. So you'll actually be able to put this into your function. So in this case, you'd have 1 divided by second square root 1 plus cosine. Now, when you push x, it should say theta now, and then sine theta. I'm sort of curious to see how this turns out. So let's see. That is what I've put in here for my r equals. It's a function in terms of polar coordinates, not in terms of rectangular. I couldn't plot that in rectangular. The one thing you need to really watch out for is when you go into window, you will see that it's either set for radian or degree mode. Mine is definitely set for radian mode because you can see that my window goes from 0 to 6.28. That's 2 pi. So that's going to give me 1 revolution. And my x min and max are sort of, in a scale. I just think I squared it up. But if you see like 0 to 360 there, then you probably want to make sure that you're in degree mode. I've turned mine into radian mode. So window, and then if I just push graph. That's interesting. Okay, so this is what I got. It looks like an ellipse. It is an ellipse, but my ellipse has been rotated 45 degrees. It looks like, yeah. So I could use polar coordinates to graph that ellipse, whereas with rectangular coordinates, no, I couldn't do that at all. I can't solve that thing for y explicitly. So we can go and graph a lot more of these things, and we'll be doing that here in a minute with polar coordinates, mainly circle things. There's a lot of things that occur in nature that are circular. Okay.
Just something as a note, I think I had brought this up back when we were doing some of the graphing, and
Yes.
radian mode wasn't like looking right as at least on mine. My ellipse got bigger when I went into zoom and did the Z trig.
Yes, that's a good point. So yeah, very good. Thank you for bringing that up. So yes, if you do zoom, and there are 2 of them that I like here for using these polar coordinates. The one that I like the most for using polar coordinates is z square, because sometimes your graph will look like it's stretched out, but z trig will also help you, and it will sort of help you depending on which mode you're in. Yeah,
it was what I had found when I was looking for making the graphs make sense. When we were doing Cartesian graphs.
Yeah.
In radians,
Okay.
It was like, yeah, but then you have to redo it if you switch modes.
Yes, that's true. That's true.
But,
Thanks for bringing that up.
I don't know why it doesn't just like apply one of those automatically so your graphs are readable.
Yeah, I think that when you change, like when you start graphing something else, then it sort of goes to what you're doing there, and then you have to go. The calculators are sort of weird that way, and then Desmos does things a little bit differently too. So you'll see when you work with that, you'll see that's more intuitive from the graphs that I've created there.
Yeah. Okay. Anyway,
all right.
Back to coordinates, I guess.
Back to coordinates, I guess. So no, we're going to do graphing now. All right, but they will be in polar coordinates. So with rectangular coordinates, or Cartesian coordinates, you describe your points there as xy. With polar coordinates, we have coordinates described by r theta, and our functions are described by r is equal to f of theta. Now, with Cartesian coordinates, when you have like an x equals something without a y, or a y equals something without an x, you might find that you get horizontal and vertical lines. That's the grid for the Cartesian coordinate system. The same thing is true with polar coordinates. So if I have polar graph with a theta and no r, what that does is it's going to sweep out a line through the origin. For instance, if I have like theta is equal to 45 degrees, and that's it, there's no r in it, then it's going to sweep out this line at a 45-degree angle, and that radius is allowed to just sweep through the points. It will have to go through the pole there, but that will be our 45 degrees. So that is what a graph in polar coordinates looks like without an r in it. So you'll get all these sort of pinwheel lines when you look at that. And that was like, these are like the chords on our spider web for a polar graph. So this is actually one of those coordinate grid lines when you don't have an r. Now, when you look at something without a theta, so r is equal to just a number, that will give you a circle. And that sort of should make sense. So if you have something like r is equal to 2, really theta can go around as much as it wants to. So the theta coordinates relax to do whatever it wants to do. It can go through all of its degrees or radians, but r is fixed at 2. So if I have a function in polar coordinates with just an r and no theta, then I create a circle graph centered at the origin. And depending on what r is, I have all these concentric circles. So when you're first learning to plot graphs with Cartesian coordinates, most likely the teacher said, hey, let's plot some points. Let's plug in some x values and create y values. We'll plot some points and we'll connect them maybe. Hey, we can do the same thing with polar coordinates. So I'm going to try this, but I'm going to need your help, okay? So everybody gets one of these. We're going to try to plot this graph. Whoops. We're going to try to plot the graph. R is equal to 4 cosine of theta using points. So the points we're going to create, though, is we plug in these values for theta into that function, and then we find what value r is. So I'm going to need all of your help. I'm going to do 0 for you, but let's see. So I'm just going on my screen. So Grace, you're going to do 30 degrees. Jaden, you're going to do 45. Connor, you're going to do 60 degrees. Chang, you're going to do 90 degrees. Nicholas, you're going to do 120. Kai, you're going to do 135 degrees. Sean, I'd like you to do 150. Jay, I would like you to do 180. And Alora, I'd like you to do 210, please. So you're all responsible for finding an r value for that theta that we plug in. And while you're doing that, I'll just do mine really quickly. So if I plug in 0, I know that cosine of 0 is 1, and then 4 times 1 is 4. So I'm going to write mine in there. Whoops. 4. Maybe. Okay. So I know I'm not giving you a lot of time here, but Grace, are you ready? What is your r coordinate for 30?
2 square root of 3.
2 square root of 3, exactly. So cosine, thank you. Cosine of 30 is root 3 over 2, and 4 times root 3 over 2 is 2 root 3. Jaden, did you get 45 degrees?
I have the decimal, but I don't have it like with the square root.
Okay, what is cosine of 45 degrees?
I got 2.82.
Okay, so that the approximation would be 2.82. That one's going to be root 2 over 2, right? So if we take root 2 over 2 times that 4, let's see, that would be 2 root 2. So 2 root 2 is approximately that 2.82. All right, great. Connor, did you get the 60-degree one?
Just 2.
Just 2, because cosine of 60 is 1/2 times 4 is 2. Cheng, did you get 90?
I got a 90 is a 0.
Exactly. Cosine of 90 is 0, and 0 times 4 is 0. Excellent. Thank you. Nicholas, did you get 120?
I got a -2.
Yeah. And now you can sort of see the symmetry here for cosine. Notice that this 60 degrees is sort of equivalent to the 120 degrees, but it's negative since it's in quadrant 2. Awesome. Kai, did you get 135 degrees?
Is it -2 over square root 2?
Okay, -2 over square root of 2.
I mean,
Yeah,
I
that
mean,
worked.
-2 square root 2.
Oh yeah, that's it. Yeah. So it's going to be just like Jaden's, but negative. All right. Nice job. Sean, did you get 150?
I got -2 square root of 3.
Perfect. So that corresponds to 30. Awesome. What about 180 degrees? Thanks, Sean.
-4.
-4. All right, Jay, thank you. So cosine of 180 degrees, we're at -1 times 4 is -4. And finally, Laura, did you get 210?
-2 square root 3.
Yeah, that's right. Excellent. So you can sort of see the symmetry. I'm guessing that if we kept going on, this would be a -2 square root of 2 because we're in quadrant 3, but we're equivalent to 45. 240, that's still in quadrant 3, right? So that would be the -2. 315, that's in quadrant 4, and cosine's positive there. And then 360, we're back to where we started. 4. So we can go ahead and plot those and see what sort of graph we come up with here. So we're plotting these in the polar coordinate system. So 4, 0 is the first one. Then I spin 30 degrees and 2 root 3. So this morning I found an approximation for 2 root 3 is like 3.46, something like that. 45 degrees, 2 root 2. Jaden said that was about 2.8, I think, 2.82. So that would be around here. 60 degrees too. All right, that's easy enough. Right there, around there. Okay. 90 degrees and 0. So that's right at the pole. 120 degrees and -2. So I spin to 120, but then I have to flip over 2. So that's going to be over here. And then 135 and 2 root 2. So I spin over to 135, but I flip through. And that's going to give me almost that 2.82, I believe. Around there. And then, yeah, 150, -2 root 3. So 150, but I flip back. And here I am about at 3.5 again. And then I hit 180 and I'm at -4. So I spin around to 180, but I flip back for, hey, I'm right where I started. So it looks like this graph is just going to form when your domain, and our domain now is in terms of theta, is between 0 and 180 degrees. So it looks like we're going to get a circle. And if we kept going, like 210, now we're in quadrant 3, but we flip back to quadrant 1, and then 235 would be around there, 240, 315 would be down here, and 360 we would spin right back to where we started from. So that's just going to be a circle. So what can you tell me about the radius and the center of that circle?
Radius is 2 and the center is at 2, 0 theta.
Exactly. Exactly. So that center over there is at 2, 0, and the radius is 2 as well. And you know what? That's going to be common for a graph where you have r is equal to something cosine theta. So when you look at that number in front of the cosine, that's going to be the square of the radius, or that will give us the radius, some indication of the radius, or actually the diameter. Let me undo that. That's going to give us the diameter of the circle. And if we look at cosine, it looks like it's gone to the right. So I'm just going to experiment around here. I'm going to plug in, first of all, we'll do that 4 cosine theta. And whoops, I'm going to delete all this other stuff out of there. I'm going to try to plot that for you really quickly. All right. So yeah, so we got exactly what we thought we would. What do you think is going to happen if I put in something like cosine or 6 cosine theta? What do you think? Any thoughts?
The circle will expand and the center of it will move over by 1 unit.
Yeah, that's exactly what happened. So if I have 6 cosine theta, it's still to the right. But now my center is at 3 and my radius is 3. So it's moved, the diameter is moved up to 6. How do you think I could get it on the other side of the y-axis, or the non-polar axis, I guess? Anybody have an idea how I could get it on the other side? Go ahead. What should I do?
Make
Could
the
you use
function-
sine?
Yeah, exactly. Let's change the sign. So what I'm going to do, okay, wait. I think I heard 2 things there. I think I heard turn it negative and turn it to sine. So, or I might have heard change its sign. So I'm going to turn it to -2 cosine theta and see what happens. That did it. It flipped it about that non-polar axis, and now it's on the left-hand side. So, okay, so here's the next question. What do you think would happen if I turned it to sine? In fact, that's our next example here. So the next example, oh yeah, but that's 2 theta. All right, so what do you think would happen if I turned it to sine of theta? What do you think that's gonna do? Any ideas?
Would it go on top instead of to the right?
All right, let's check it out. So I'm going to do 4 sine theta. 4 sine theta. That's exactly what happened. Nice call. So it looks like if I have 4 sine theta, that's going to create a circle of diameter 4, but it's going to be up. So maybe like -4 sine theta would flip it down, right? It does. Okay. Now we could figure out what's going to happen when you put in a double angle. And that's what I'm looking at here. Any thoughts about this one? So I have sine of this double angle. Notice what I had to do with my degrees. I had to cut them all in half. Even like the special one. So to get 30, I had to plug in 15, and 45, I had to plug in 22.5. That doesn't seem right, but I had to do that to get enough points. So I'll sort of show you what happens here. It's called a rose graph. So we have this rose, but interestingly enough, it looks like it has 4 petals, but the theta is only 2 theta. That's sort of weird, right? So sine of 2 theta will give me this 4-petaled rose. So if you went through and plotted some of those points, you should find that rose graph too. For this one, you'd have to go through the whole 360 degrees to get that rose graph. So in conclusion, we can get these sort of famous graphs. And when you do the Desmos project, you'll be able to experiment with some of these. So the rose graph, notice the cosine 2 theta gives us something that's sort of symmetric with the y-axis or non-polar axis. And the sine graph gives us something that's sort of tilted at a 45-degree angle. And we get double the amount of petals when our angle is even. However, if you look down at sine of 3 theta and cosine of 3 theta, you get exactly the same number of petals if it's odd. And those graphs only take 0 to 180 degrees to map out. So these are called rose graph, or 4-leafed roses, 3-leafed roses, very pretty. Of course, like the A will give you like how far you go out. So the A out in front sort of controls your radius. What other sort of graphs can we make? We couldn't make any of this stuff with Cartesian coordinates. The lemniscate. So the lemniscate is sort of like an infinity or an infinity on its side. And that's what you get when you have r squared is equal to a cosine 2 theta or a sine 2 theta. Again, that sign is tilted. So those are some graphs you can get when you have r squared is equal to cosine of a double angle or sine of a double angle. Finally, maybe my favorite, cardioids. So if you add something on to a cosine theta or a sine theta, then you create a graph that looks like a circle but has a little dimple in it. And if you know anything about cardioids, like cardiac arrest, it's like a heart attack. Cardioids mean heart. So these are nice little heart graphs. They're heart-shaped graphs. They have that little dimple that looks like a heart on them. So those are cardioids, and we get that when we add a constant onto a circle. Sort of weird. In fact, you know, if you do that Desmos project, you'll get to experiment around with these. Some of them you can actually get like a loop in the middle of them. So these are sort of weird, neat graphs that you could never ever get if you were graphing with rectangular coordinates. A lot of these things sort of do occur in nature.